So let's apply this to a simple situation first. Let's imagine an acetic acid acetate buffer. We just had the pKa value for acetic acid recently up on the screen. Let me get that number again. I have it over here. It's 4.56 for acetic acid. Let's imagine we have 0.1 molar of each. So that meaning our concentration of acetic acid, CHCOOH, is 0.1 molar that we prepare it with, and the concentration of acetate, conjugate base, is also 0.1 molar. So I've got the Henderson-Hasselbalch equation up here still, so let's use it. So pH, the pH of this buffer is going to be pKa plus log base 10 of our concentration of, and I always have to double check this, it is the base that goes on top, acid goes on the bottom, A minus over HA. And so we can write A minus here being acetic acid, or acetate, HA being acetic acid. Okay, so pH, we can plug in our pKa, 4.56, plus log base 10 of 0.1 divided by 0.1. Now these have units, but because this is from an equilibrium expression, those units will cancel out anyway. Okay, so let's find this log term, the second term here. So this is going to end up being log base 10 of 1, and that is equal to 0, just by definition of logarithms here. You can plug this into your calculator to double check it. So the pH will be 4.56. And this is in general true for any 1-to-1. If we have a 1-to-1 ratio, not ration, but ratio, 1-to-1 ratio of HA and A minus, then the pH will always be equal to pKa. And that's just the way the math works out in the Henderson-Hasselbalch equation. So that's sort of like a good starting point in terms of a buffer. And this is actually the best place you want a buffer. You want a buffer right at where the concentrations are about equal to each other. You can adjust the buffer from here, all right, but this is sort of like the natural best place for a buffer to work. What if we, say, had a different ratio? What if we instead had 0.1 molar of our acid, but only a tenth of that of our base? All right, so 10 times higher HA to A minus. All right, so we can plug this in again to a Henderson-Hasselbalch equation. All right, the base goes on top, 0.01 over 0.1. So let's just look at this term here. We'll get the log of 1 over 10 of 1/10. This will give us a value of -1. Again, you can plug that into your calculator to check. This is a nice property of logarithms. If things change by factors of 10, for the base 10 logarithm at least, the logarithm will change by a single unit at a time. So that will give us 4.56 minus 1, which is equal to 3.56. And that'll be the pH of a solution where there's 10 times more acid than base. So we'll get an increase of plus or minus, a -1 in this case. If it was the other way around, 10 times more base than acid, then we get a +1 change instead. So these are some sort of benchmark points that you can think of when thinking about concentrations of acids and bases and in a buffer, and sort of benchmark values that you can kind of compare to.